Okay, so eutectic is a point where you have two different solid from a liquid change into two different solid alpha beta. Then you have a eutectic point. And also there will be a pro-eutectic point over here where your liquid changes to the first alpha for parenthetic alpha here. And if the line fall on here, then you have a pro-eutectic beta here. Right? Okay. So by now you should be able to do the level rules or the trade line, the tie line. Today we learn another name called perithetic. Okay. Perithetic is a reaction by this chemical reaction. Liquid plus alpha solid. You cool down, you get beta solid. Okay. Okay. So earlier, eutectic, eutectic reaction. You have liquid, then you have temperature and cooling become alpha plus beta solid. Okay, today we go perithetic. Okay, perithetic is from liquid plus alpha. You cool down, you get beta. Okay. So eutectic, you get liquid become two solid. Perithetic, you get alpha plus solid become solid, another solid. So commonly present as part of the complicated binary diagram, particularly if the melting point of two components are quite different. Okay, so if you look at this diagram, phase diagram, this is a nickel weight percentage of nickel. So this graph from 0 to 9, that is a weight percentage, WT percent of Ni combined with ferrum. So this temperature, you're given liquid on the top, gamma, delta on the left, and there is a middle here is gamma plus delta. Here a little bit of liquid plus gamma. Here is liquid plus delta. So okay, so here is gamma. So here, this line here is gamma plus delta. So here is gamma plus delta. Okay. Then you look at the temperature. Can you see eutectic reaction here? And on this graph, on this phase diagram? Is there liquid to solid? You don't have, but you have paritatic reaction where liquid plus one solid become another solid. Okay, liquid plus alpha, it can be anything. Liquid plus alpha, then it will become another solid, which is this one. Okay, so there are two solid phase, delta gamma, delta gamma, delta gamma, and one solid phase. Okay, so in this case, your delta phase solid solution, nickel is in BCC. This one is in BCC. Gamma is in FCC. So it changed from crystal structure BCC to FCC. Paritactic temperature is 17 here. 1517 is here, this temperature. So here is liquid plus solid become another solid. So you can see this line, liquid plus one solid become another solid. So here, maybe to here. So around this line. Okay. So paritatic temperature 1517. Paritatic composition of 4.3% of nickel in iron defined as paritatic point C, which is here. Okay. So here you read from the graph. So here alpha plus gamma, or the first type of solid, L plus delta become gamma, which is this region is gamma. So as long as this section cross to the solid, in this case is point C, you extend to the left, you get the temperature. Okay. So to solve this phase diagram, usually we will ask you to write the equation first. Write the reaction equation, either eutectic or paritatic. Then you find where is the point of the either eutectic or paritatic. Okay. So here is quite complicated because at this point you will see three phases, delta, gamma, and liquid coexist in equilibrium. This one, because this point C, on the top here you see liquid delta, below here you see gamma, on the right here you see liquid plus gamma, below here you see the mixture of gamma and delta. So here is a triple point. This is a triple point. Point C is a triple point. So here 4.3% nickel, or 4.3% nickel combined with 95.7% of ferrum. Pass through the temperature of 1517. So the one that I highlight with the small box here is called paritatic reaction. So liquid plus delta, you cool down at a paritatic temperature 1517. Remember to write the word cooling. What do you see at the solid? Another solid. So here liquid, how you find the liquid? How you find the percentage of liquid of nickel? You extend this one to here, this line. Then you extend down, you get 5.4. How you take gamma is this point. You extend down, you get 4, about 4. Then gamma is 4.3. Okay. So now we consider what happened if we drop temperature from point A to point C. Okay, you cool down, start cooling from 1550 Celsius, slightly below. Then you cool down just below the parenthetic temperature, A to C. So from 1550 point A, you cool down to point B, about 1525. The alloy cool down from liquid, and then the first delta form in point B. First chicken pox form in this point B here. The chicken pox will be delta solid. Okay. Then you drop down from B to C, the delta of 4%, the delta of 4%, and liquid of 5.4% nickel is in equilibrium. Okay, so who don't understand point C, this statement? This one is read from this line. 4 is the delta solid phase. This one. Then another on the right is 5.4 liquid. So recall all these parenthetic. So you can use level rules. You can use level rules to find how many percent of so and so liquid and solid. So again, on the left is called hyper. On the right is hypo. Okay. No, on the left is hypo. On the right is hyper. Okay. So if an alloy in ferrum nickel system is less than 4.3% and is slowly cooled from liquid state through the liquid plus gamma region, there will be excess of gamma phase after the parenthetic reaction is completed. Okay, so if the ferrum nickel system more than 4.3 nickel but less than 5.4%, yeah, the nickel will slowly cool from liquid state through the delta plus liquid region here to here. There's a triangular here. Okay. So then, if in the yellow color box here, there will be excess of liquid phase after the parenthetic reaction is completed. Okay, so these are another diagram for silver and PT, platinum. So this one is a phase diagram for silver, 0 to 100% silver Ag. Okay, so all these bubble, or we call it state diagram or equilibrium diagram. So let's say alloy 1, from dot number 1, number 2, number 3, you should able to understand what is this. So point 1 is liquid phase, so nothing there, but you need to label what is the empty space. Then the second point here already enter into liquid plus alpha. So you circle, then liquid alpha. The third one is over here. You already, this point, you already reached the maximum point of no more liquid, but it start to go into alpha plus beta point, or you can say as 100% beta here is pointing this one. You go to here. Okay, so this point don't have. This point actually quite confusing. This point, if you enlarge this one, you will see the region of beta still pointing here. Then if you shift to another one on the right here, here will be liquid plus beta over here. Okay, so this one is quite direct lah, huh? So we want to find the peristatic reaction in the diagram. So again, peristatic is liquid plus one solid become the second solid. So you go and find on the diagram, you go and find the region of liquid plus one solid first. In this case, you have liquid plus alpha. You can find this one. Then you go to this region, form into beta. So here to here, right? Here to here. This will be the alpha become beta. So there will be one point that is become beta, which is here. So once you find the point, you extend to the left, you'll find the temperature. This one just slightly below 1200 degree. If you enlarge the graph, you'll find about 1200 degrees C. Okay, so here you expand down, you'll get 42 point something silver. Okay, so this is what happened if you decrease the temperature. So here, when you have peristatic, you see the diagram. When it become in a solid liquid, in a liquid plus alpha, you draw liquid and alpha. But when it form into, before it form into alpha beta form, which is here, this point to this point, the beta will form outside the layer A. It will be like the supercool reaction. In this case, it's peristatic, so it will have one layer outside. Then, as it grow, then it change into beta. It will change to beta. Huh? So you take again this peristatic reaction, liquid plus alpha with the horn, and this is a process. And then at the end, you get beta. This one. So during the rapid solidification, means you rapidly cool down, you will form another layer of a cast iron through a peristatic temperature, a non-equilibrium phenomena, which we'll see this encapsulation happen, or coil surrounding or encasement happen. So you will see one layer if you have non-equilibrium phenomena happen. Okay. So there are two behavior happen. One is from the liquid form will form the beta, or another one, the alpha inside will change phase, alpha become beta. There are two directions. One is from the liquid change to beta, and the one is from alpha change to beta. So at the end, total, you get beta. So liquid change to beta, alpha change to beta. Okay, so that is a peristatic process. Okay, and you have this encapsulation or this encasement is because you do it in a non-equilibrium condition. Means you rapidly cool it down. All these are the chemical lah. So when beta form solid phase, and if you solid diffusion relatively slow, you will create a barrier, right? So you will see The dashed line, this one, alpha 1, alpha, alpha, 2, 3, 4. This is rapid cooling. This one also. Beta, this dotted is a rapid cooling. So when you have rapid cooling, you will form the core. Okay, you will form the core. So this is a schematic diagram on how the encapsulation happen. So you'll see this kind of microstructure. Dark one is beta. Residual is light gray is the alpha. So this light gray here. Right. So let's see how the question will look like if the question asks you peripatetic phrase. So again, the example 6 here, it asks you to do phrase analysis. So phrase analysis, there's a standard template there. So you calculate the phrase change, state change, and so on. So you're given this diagram. Of course, in the test, the bubble will be removed. The tie line will be removed. Alloy 1, alloy 2 will be removed. Okay, so this one, it asks you a point at 42.4% Ag and 1400 degrees C. So to solve A, you go to the diagram, find the temperature, draw a line, find the percentage of the silver or Ag, draw a line, so you get an intersection point there. When you draw an intersection point, okay, you draw an intersection point at this one, you draw a tie line, you draw a tie line again. So tie line here on the left is alpha, on the left is alpha, in the middle here is liquid plus alpha, on the far right is liquid. So in this tie line, you only have two components, alpha, liquid, or alpha liquid. Okay, but this tie line, it depends on this point. So this point, you can calculate the total length. So total length, you have two sides. Left-hand side is to calculate the liquid. Right-hand side is to calculate the solid. It's the same concept as the tie line you learned before this. So you draw the line and then drop down. There's a percentage there. So you write below the graph here, 7. And then you drop down this one. You find 55. You write 55 there. Okay. You follow the template, right? 7, 55. Then you write the template. Okay. So A, 42.4% Ag at 1400 degrees C. First phrase present, you have two phrases there. Alpha, solid, and liquid on another side. Alpha is over here. Liquid is over here. Then second line in the template, composition of the phrases. So alpha, what is the composition? Read from the graph, 7% Ag bracket alpha. Liquid, drop down, 55% Ag liquid. Huh? This is 55%. On this graph is silver, Ag. So this one is liquid Ag. Huh? It's important you write what is the name of that one. Huh? Don't write PT. Huh? Don't write wrongly. So the third one is amount of phrases. You need to calculate amount. Okay, amount of phrases is using tie line equation. So solid is what? Here divided by total length. So it's about what? 55 minus 42.4 divided by 55 minus 7. Multiply 100. Okay. Who don't understand how to get 26? Who don't understand? Okay. Huh? So for another side, if you're lazy, you just take 100% minus this one. If you're lazy to do, it's 100% minus this one. Of course, you write 100% minus 26, you get one answer. Or you can do another calculation. This side, 42.4 minus 7 divided by 55 minus 7. Okay. You add up, it should be 100%. Huh? Okay. So if you understand this one, you look at B, you look at the procedure rather than the numbers. If you understand, it's okay. Now, B is 42.4%, 1187 plus delta T, means above the important temperature. In this case, it can be parenthetic. It can be eustatic. You need to read the diagram. In this case, is you are at the alpha plus liquid plus alpha, and you are seeing beta. You are seeing beta here. So this is parenthetic temperature. Okay. So you look from there. Just above the T, just above. So you just copy all the, just above the line. So you just go to the line, shift your horizontal line up a little bit from 86 up a little bit. You will see 66.3, and here is a little bit about 1,200 degree. So you will see 66.3 on the liquid side, and here is about 10.5, about there. Okay. Sometime in the exam, we will just give you the point. You just need to know the key there. There must be a reason why the question suddenly one number is there. Okay. So again, repeat the template, phrase present. In this case, you have a liquid phase on the right, alpha on the right. Okay. Composition, just read from the graph. How many percent liquid? 66.3% liquid, and is Ag liquid. It's Ag liquid, not PT liquid. It's Ag liquid. Alpha is, read from the graph, 10.5 solid alpha. Okay, 10.5%. In this one, you should write 10.5 WT. WT, because this one is weight percent. WT. Amount of phrases using tie rules. Right, the 7% WT. So again, this liquid, so you read from this side, here to here, divided by total length, because you're looking at liquid. You look at alpha, you read from here. Okay, or if you, for the solid, you lazy, you just take 100% minus 57%. But it's always good you do the calculation just in case you do some wrong calculation here. When you check it's not 100%, then you have chances to check your answer. Okay, what about the minus T? Means just way below the 1186. So just below. So just below. You're still seeing just below this one. Just below this point. You only see beta just below it because it's still touching this point. Okay. Again, this one, 1187 is a parenthetic. Parenthetic, you are arriving at 1 second solid on the right-hand side reaction. Okay. So here, this question, You look at the question, you are at the zone of liquid plus alpha. If the temperature just below 1186 means the temperature will be around 1185, 1184, just a little bit of delta temperature. So you will be arriving at the parenthetic right-hand side equation, which is beta. Okay, or another solid lah. Here you read from the graph will be 42.4% Ag beta solid. Amount of phrases 100% beta. Okay, this one. Yeah. So don't confuse this one with the early one, eutectic graph and the parenthetic. So C, it gives you another new point, 60% Ag, which is on the graph, 60%, at another new temperature, 1150. 1150 is about here. So you draw a line, 50%. You draw a line, you will get a tag line, a tie line. So every time you see a tie line, extend down, write the percentage, extend down, write the percentage. Have that kind of habit. Then it will help you to calculate the phrases. All right. So again, repeat the template. Phrase present, you move to the left and right of the tie line. On the left, you see beta, alpha plus beta. On the right, you see liquid. So the phrase will have liquid and, sorry, in this case is it touching the line. It touching this line is beta. Not yet go to the alpha plus beta. In this case, this line is beta. Okay, so the answer for the D, you have two phrases, liquid plus beta. Don't overread. Don't overread. This one is parenthetic diagram. So composition, read from the graph. Liquid will be 77%. Beta will be how many percent? Okay, I haven't give you the attendance list. Muhammad Rasid, what is beta composition? What is beta composition? What is the liquid composition? How many? I ask you composition, not temperature. You understand composition or not? You know what is the word composition means or not? Huh? You know weight percentage or not? You know how to read this graph or not? You understand 77? Huh? 77 what? Huh? weight percentage is what? Okay, is what? Solid or liquid? Liquid. Beta? That is a composition. Composition is how many percent of weight you have. This one important. This is a very popular question for phase diagram. If you don't understand, it's very hard for you. Okay? Stop me if you don't understand 77 and 48%. Okay? Amount. Don't confuse with composition and amount. Amount is calculated from the timeline. So liquid how many percent? Can some of you calculate? How many percent of liquid in the at 60% Ag and 1150 Celsius? How many amount of phrases of 77% liquid Ag? 100%? Anyone? 100%? 41.38. Okay, so if you get 41 point something, beta will be how many? 50. Okay. So about 41 point something lah. So this one is not accurate. In your answer, you should give about three significant number or 3 decimal place. Okay, so roughly you know lah. So these are important template lah. So if the question asks you phrase analysis, means you need to start with phrase present, composition, amount of phrases. Yeah, these are the template. And we will mark accordingly to this one. Okay. Next, parenthetic, we'll learn about monothetic. Monothetic is liquid become alpha plus liquid. Yeah. So mono, third one, mono is liquid 1. You cool down at 1 temperature, you'll get liquid 2 plus alpha. Liquid number 2 means different liquid already. Okay, this is called mono. Mono means you start from 1 liquid or 1 state. In this case, in liquid, become liquid plus alpha. Okay, so this one will be the previous one, parenthetic, eutectic. So this one you can find in a copper lead system at 955, 36% Pb. Okay, so Pb. So where does this monothetic happen? Mono is liquid 1. You cool down, you get liquid number 2 plus 1 solid. So you have liquid, you have alpha liquid, you have alpha beta. Okay, so here you look at liquid 1 become liquid 2 plus alpha. Okay, so there's one point here, this dot. Liquid cross to this, because you cross to here wrong already. L cross to liquid plus liquid 1, liquid 2. You have 2 liquid, not monothetic. Here, liquid cross to here, alpha plus liquid 1. So it also do not meet the definition, right? This one we unable to tell whether it is a liquid 1 or liquid 2. Yeah, so this one is liquid 2. Then this one is liquid 2 lor. It's the same region, so I think it's liquid 2.
There is no like a definite
Maybe no research over this region. No research. So there's an overlapping of L and L2. Okay. So here, as a result, terminal 0.07 copper. Form at room temperature. Okay, this one later you look at bigger than C. So this is microstructure of monotactic alloy. You only see one kind of copper. Okay. Okay, so this one, how we strengthen the material, we add lead into the very small amount. Okay, so this table is important for your revision. Okay, this table is important for your revision. It won't given in the test, so you need to memorize this one and put inside your. Right, just go look at this one when you do revision. Okay, so equation will be liquid for eutectic is liquid plus alpha beta. So this phase diagram characteristic is where you look at on the graph, where you look at. So you look at alpha at the left, beta at the right, and with the liquid in the middle. Then for paritatic is alpha plus liquid, then become beta. So you look at alpha liquid, and then there's a beta below there. Because on the top here show liquid one, liquid or liquid alpha. Okay. Then monothetic is liquid become alpha and liquid 2. So you will see liquid 1 above, liquid 2 at the side, and alpha. You look at this region. Then another one is eutectoid and peritectoid. It's the same concept, but you look at alpha become beta, gamma. Peritectoid is a reverse of, not reverse, but it's a alpha plus beta become gamma. So this one is solid become the third solid. Peritectoid, you can see as a solid. You have a toid there. Means you look at the solid 1, solid 2 become solid 3. So here, eutectic is 1 solid become 2 solid. So you look at different. So eutectic is always start with 1. You have a U1, EU. You always have 1 on the left. Peri, you have 2 on the left. Mono, you have 1 on the left. Okay, so this is an important diagram. Important diagram. The rest is production of in the industry. This one is add-on information. You can go into YouTube and look for how the production of ion in the blast furnace. This is just a short introduction in diagram. Okay. So let's see if you manage to arrange one technical visit. If not, then you just watch YouTube. In the industry, the carbon they call coke in the mill, in the iron mill, in the iron factory, when they mention coke, it means carbon. So there's a process. There's a process. Another one is in the oxygen furnace. They blow oxygen inside the furnace for oxidation. This is another process, steel process. Okay, another very popular carbon system, which is we take ion carbon system. So this is an ion carbon system, also one of the popular diagram we always use in the test because it's so in all the product there outside there, you can say 90% they are consist of carbon steel. Right. So this is the presentation of phase diagram for carbon steel. So this is weight percentage of carbon. So the more you move to the right is carbon percentage. Then you combine with the ferrum ion. Okay. So for the carbon steel phase diagram, it won't go very far because you don't need a lot of carbon to make the carbon steel. Because you add more carbon, it becomes brittle already. So it lost the purpose of using steel. Okay, maximum on this graph will be 6.67% of carbon. Maximum carbon. So here you see a lot of phrases. Liquid plus solid. Ferrum 3 carbon is a solid. Gamma ferrum. This is gamma ferrum. Ferrum carbon. Alpha ferrum. Okay. Another name austatite gamma. Okay, the way you read it will be the same as what you learned previously. Complicated part is on the top here. This one usually will enlarge this portion for your analysis. Okay, so just for info, Fe3 ferrum 3 carbon is very stable and were treated as equilibrium phase. Okay, these two diagram actually is the same diagram. It's only stretched on the left red line one is stretched longer. On the right is squeezed further. Actually, it's the same graph. Right? The shape is the same. On the left graph, just be careful when you read. On the axis, on the left, y-axis is Celsius. On the right, y-axis is Fahrenheit. On the top is atom percentage. On below is WT percentage. This kind of question can combine with weight percentage in AT percentage. Okay. Okay, so the rest you read because it's only the concept is the same. It's only a few new names. For example, gamma here, you read from the graph. Gamma is austenite. Cementite is this one, Fe3C is called cementite. Delta is called ferrite. Okay. Way all these names, you'll see question come out, we will tell you what is this. Okay. So this is just tell you alpha ferrite. So this one you learned in the crystal structure earlier. You have alpha ferrite bracket BCC, so on. So alpha ferrite is over here, very small portion. So just need to highlight the solubility. Solubility is here. So alpha solubility is 0.022% over here. Means solubility of carbon. very, very small percentage of carbon can only dissolve in alpha at that particular temperature, 722, this one. Okay, this solubility of carbon in the alpha. Okay, so from here you should able to see what is the maximum solubility when you have a delta. You just extend this one, go down, you get 1% at 1495. Okay, the question will be ask you whether you know how to read the phase diagram. It will ask you what is the maximum solubility of something at what temperature. Okay. Austenite, all these things you read lah. So austenite is this line, gamma, this line. So austenite have FCC crystal structure. Yes. Yes. You see the maximum here, maximum dot here. For example, alpha is here. 0.022% of carbon can dissolve in here at this temperature. Okay, so for example here, austenite at this line, 1147, you extend down, that is the maximum, like for example, 2% carbon at this temperature. So here, same, gamma, you extend down, here got 1%, very, very small, at 1495. Okay. So this one, solubility of carbon, 2.1%, 1145, 11, about here. Okay, so it's 2.1% of carbon can dissolve in this, means can fit inside the space here. Cementite, Fe3, 6.6%. So this it will be the maximum 6.63% carbon and fluoride. So this Fe3, the whole chart, because we in the industry we don't use more than 7%. If more than 7% become too brittle, you knock it, it crack already. So we don't want that properties. Okay. The rest you read, The rest you read. So paritatic, really explain to you what is paritatic. So this one you read, and then you try to understand what does the process. Okay. Eutectic also same. You read from the graph. Liquid become too solid. Eutectic. Eutectoid. Eutectoid means solid. One U means one. One solid become two solid. So especially here, go and read. Eutectoid also, U become one. All right. So carbon less than 0.77%, 0.77% of this one is called hypoeutectoid still. So because this point is called eutectoid process, so eutectoid on the left, on this point on the left is called hypo, on the right is called hyper. Okay. Okay, let's look at this application. So if you're given a chart, a carbon steel chart, right? So carbon steel chart, you're given 1%, 0.77% C is slowly cool from one temperature, 750 Celsius, to temperature just slightly below 727 with this line actually. Then it tell you is 0.77%, which is here. So you draw the line, Then you look at this temperature. Then what do you get? Huh? Assuming austenite is completely transformed to alpha and cementite. Calculate weight percentage of eutectoid ferrite form. So you prepare the template like just now. Then you do analysis. So we're looking at this region. So you draw a timeline. Draw a timeline. Draw a timeline just below 727 because the dot is just below here. Right? Draw a line from alpha boundaries to Fe3C, which is cementite boundaries. So you draw from alpha, draw to cementite. Then you start calculating the weight percentage. Yes. Yeah, it's all the way to the right. But on the graph, you only need to pay attention to 6.67. Well, that is amount of solubility in the firm. So percentage of ferrite with alpha will be, you take maximum point. This is a maximum point to this point. So 6.67, and this will be 0.022, not mistaken. Okay. So the total length is from 6.67 minus 0.022 is the total length. So you're calculating for right with this point. So you are taking this length. So you get 88.7%. Calculate weight percentage of eutectoid cementite can form with this. You take minus 100%. Okay. It's a different arrangement of structure. If you use the template just now, it will be the same. What phrase appeared, what is composition, and then what is the percentage of weight percentage of that. Okay. Example 7 is the same diagram. So this one, your homework lah. Go and see. So if you understand example 7, this one I should label as example 8 lah. I changed already. Changed already. So example this AB you go and find. Okay, and read. It's actually the same process. Okay, carbon steel. Slow cooling of carbon steel. So if sample of 0.7 eutectoid, 0.7, this one is enlargement, this point is enlargement of this section. This small section, it enlarged into this section. So carbon steel of 0.07, 0.77% plain steel heated about 700 degrees C. This one is 700. 750 is about here. This point is 720. And held for sufficient time, the structure will become homogeneous or authentic. This process is called austenite. Don't know how to read. So it's called these names. So it actually is a process of strengthening the material. Okay, the rest you read. At point B, when it reach below 727 degrees C, a structure called pearlite, like a pearl, will form. Right? It will form something like this under microscope. Okay, so what is important about these slides? This slide is to, if the question asks you about this section, this process. When the question focus on 727 degrees C or touching on 0.77%, it's actually referring to these slides. The question asks you what going to happen, why the microstructure just below the 727. The answer is polite. The question actually want you to write polite. Okay, this is another illustration. You drop from A to B. A is gamma, so you have all the gamma solid. Drop below 727, you get a perlite. Okay, the rest also same. You read lah. Read lah, same. Okay, so the rest also same. What is important, you should able to know how to draw the bubble. Okay, the microstructure equivalent diagram from C, D, E, F. Okay, this is another presentation. So this go and read lah. So this one, another one. Hyper. Hyper means on the right hand side of the eutectoid temperature or percentage. This one is if you are in the factory that makes ion, you need to refer to this chart. This is the overall chart, like encyclopedia lah. How many percent you need to mix the carbon to get what you want. Okay, so this is a crystal structure, BCC to FCC transformation. This is another one. The detailed one you can see in the appendix. Example B, you go home, go and read. Actually, the procedure is the same. Go and read. Okay, so this one is just tell you to reverse the revolutes. What is the X value? Okay, you need to find like how many percent of carbon that form the hypo-eutectoid steel. Okay, homework. Heat treatment is how to make a steel become more and more stronger. This one also you read lah. It's information for you. How to get martensite. Okay, martensite. So you just read the phase diagram for austenite, become martensite. So this one you read. This one also you read. Hardness, you read. And these are the table that you can use. What is important is that by the end of this lecture, or after you pass this module, you should be able to know that there's a code for the steel. If you buy steel, you work as an engineer, you need to order carbon steel. So there are code there. So this is AISI SAE code, and you can find this one on the encyclopedia. Okay, the vendor will give you all these parameters lah. For example, 1010. What mean by 1010? 0.1% carbon, 0.4% Mn is can either cold roted or hot roted, and this tensile strength, yield strength, percentage of elongation. They're able to see what are the application. This one you memorize. Like for example, from austenite, how you get perlite, how you get binite, how you get martensite, how you get tempered martensite. This is a flow chart. Okay, how you memorize. Huh? If the question asks you, what is the process to get austenite to perlite plus alpha by a prothetic phase, you just say that you only need a slow cooling process. Okay, or moderate cooling or rapid quick squinch. And then how you get tempered martensite. You rapid squinch, you get martensite. You reheat again, you get tempered. Okay, memorize this transformation diagram. Huh? The rest is just for your info. As long as you understand there's a code for the metal that you're buying. There's a code there. Okay. So different code, different arrangement of numbers. So AISI is 4 numbers. BSA, British Standard Association, they have 3 numbers. They have a 6 number there. 070M20 means something. We won't test you what is the meaning of this one, but when you go out to work, at least you have some ideas what actually your boss or your customer saying about. Okay. Stainless steels, only you need to remember. Stainless steels, one very important ingredient is chromium. I only need to remember this one. Okay. How many percent it become different type of stainless steels? Okay. So what differentiate from carbon steel to stainless steel? Chromium. Stainless steel or carbon steel don't have chromium, but as long as you add in chromium, the name become stainless steels. Okay, the rest you read lah. There are 4 main type of stainless steels: ferritic, martensite, all these things. So you read. Lots of theory. So this one you read lah. I won't ask you this one, just for your info. Important that is how you get stainless steels is add in chromium. Okay. This one you read lah. All this information you read. Okay, with this we conclude chapter 9. Okay, so we already completed your CL3